Ya no hay eco, me parece, ¿no?
Ahora está mejor.
Sí. Vale.
Welcome, Pasi from Finland. Welcome, Fenchong from China. Hello, Galina,
Hello, Rosa.
Elisabetta. Hello, Pasi.
Ok.
Ya no hay eco, me
Hello,
parece.
Anna. Oh, Lilith. Hello.
Vale.
Welcome, Pasi from Finland. Welcome, Fenchong from China. Hello, Galina.
Hello, Rosa.
Everybody. Hello, Pasi. Petia.
Ya no hay eco, me parece.
Hello. Silvar. Hello. Welcome, Pasi. Welcome.
Ok.
Ah, Enoch. Hello, Enoch. Korea.
Ok.
I see you.
Ahora estamos transmitiendo, Ricardo, y Rosa. Así que cuando
Hello.
deseen,
De
esperamos
acuerdo.
hasta y
Okay.
5.
Welcome, Corina. Privatus, welcome. Petia.
Oh. Thank you so much.
Hello.
Welcome for
Hello,
everyone.
Hello.
everybody. Hello, everybody.
Hello.
Bruno is my colleague from France, you know. We are working
Hello.
together.
Thanks.
Bruno.
Thanks for this meeting.
Hello, Bruno.
Apparently, you know all each other. I'm quite a newcomer. I just know Dr. G.
More or
which is-
less, no? I think that we are a group of friends that we have contacts from many occasions, and then, well, it is nice, very nice.
Okay.
We are waiting to be everything ready.
Beatriz, voy a compartir pantalla.
Con
Okay.
todo gusto. Ya estamos transmitiendo, después yo voy cortando al principio lo que no nos parezca, pero me parece que está todo bien. Así que adelante, Ricardo, si querés.
Hello, Salma. Okay.
Hay un...
Se ve
Se ve bien. Ujú.
Well,
Rosa, tú, cuando quieras. No sé.
well, maybe we can begin, okay? Well, welcome to everybody. This is a wonderful occasion to exchange our point of view, our opinions, and to begin to prepare the project UNESCO NASE project 2026. As you know, the title is Find Your Exoplanet, and we want to involve the students in all the countries in the world to try to learn a little bit more about exoplanets and to have the opportunity to do some different activities and also to discuss between them and to try to find their exoplanet, the favorite exoplanet that they try to discover in a list of we proposal or in the website of the file that exists in NASA facilities. Then I would like to introduce Beatriz Garcia. She's the boss, and I would like that Beatriz say something to us?
Yes,
Also,
of course.
she
Oh, yes, thank you.
control everything.
Thank you,
Beatriz.
Rosa. And it's a pleasure to be here and to see all the friends all over the world. And well, I hope you enjoy this proposal, which is I found is very actual and interesting, and it's a moment to talk about more about our planet and the importance to preserve that planet, which is the only one we have. The other thing I would like to share is that this year we have the Latin American meeting of astronomy in Mexico. And I will invite you to prepare good presentations and projects to send the contributions to the Latin American meeting in this way to make shortest the distances between the countries and to establish better bridges between cultures. The meeting will be in December, so before the meeting, the Latin American meeting in astronomy, we will have our closing ceremony of bridges between cultures. So would be great if every one of you prepare something for the Latin American meeting of astronomy, and we go to Mexico online. If you don't have money to travel, the meeting is online also, will be hybrid, to show your work in this opportunity. So this is also an invitation, not just for this activity during 2026, find your exoplanet, but also to prepare your participation for our meetings here in Latin America. So thank you very much, everyone. And Rosa, you have all the space and the stage.
I would like to ask to Ricardo, if it is possible to show again our timeline that we have a few minutes before on the screen.
Yes.
Well, the main idea is that all of you, Ricardo, we can see, but in a very strange format. Okay, well, the idea is each one speaker invests 10 minutes, and after we have 5 minutes for questions. Okay, and I would like to mention that in this session, we organized the presentations in some way in two groups. The first part is the slide number 3. Ricardo, if it's possible for you to show us. The next one slide. Well, the next one, number 3. Well, the idea is that we have a set of different contributions in order to explain essentially the project. Okay. At the beginning, Ricardo explained to us how to use the activities with students and how to send to us the reports and the information. After that, we have 2 presentations about several activities that we promote with the students. And also, after that, we have an example of how to find this favorite exoplanet I mentioned before. And also we have one explanation about where you can find candidates in order to choose what is the best option. And the last slide, Ricardo, please. Then next slide.
Yes.
Yeah, last one. Okay. Pásame la siguiente.
Sí.
Yes. Then, in this case, we have several reports from different countries that present examples of life in very extreme environments. Then we have a couple of examples of life in the desert. Also, we have one about the situation in the very, very cold areas like the north of Lapland. Also, we have one special presentation about one environment with a special level of acidity in Rio Tinto. And finally, we have one example in Mars, because this is one activity in Mars, because we are practically working about this planet that we hope to arrive there. And also the life in extreme conditions by Margarita Metaxa. Well, you can see that there are some contributions about to try to find a planet B, but I would like to insist that this is not easy. The most important is that we continue in a good situation with our planet, that in this moment is the only planet that we have, okay? Then this is essentially a summary of our general presentation, okay? In this, our timeline in this session. Then I would like to invite to Ricardo Moreno to begin with his presentation. You would like to explain to us how is the method in order to send the results for the different teams of people in the different countries. Okay.
Okay.
This is your turn, Ricardo.
Sí, okay. How to participate in the NASE-UNESCO project. There are two documents that can be downloaded from the NASE website. The first is a 10-page introduction that the teachers should read. It includes explanation of the knowledge involved in the project, and also provides instructions for completing the 4 proposed activities. These activities will be explained in another presentation today. I just want to clarify now that in the last activity, the 4th activity, you have to choose an exoplanet. With younger students, the easiest and most recommended option is to choose from the 30 candidates in a table included in the teacher's document. Older students can search for it on a NASE website specific about exoplanets, which will be explained in another presentation. The second document that must be downloaded from the NASE website is the one we will use to complete the report, and it is 5 pages long. You must submit the report with the teachers' and students' information, and includes 3 photos within the report. The photos should show the students performing the activities to prove that they did them. Let's see how to fill out the report. One moment. On the first page, fill in the fields for the authors, maximum 3 students, and the location where the activities took place. On the second page, click inside the box and then...
Sorry, Ricardo, we don't see what you are doing. and appears another PowerPoint. I think
Okay.
we have here. Okay, now it's good.
Okay. On the first page, fill in the fields for the authors, Ricardo Moreno, for example, maximum 3 students, Ramon Garcia, Antonio Perez, Manuel Lopez, and the location where the activities took place. For example, Colegio Retamar, Madrid, Spain, the day, month, in an hour, and latitude of place. And the second page, click inside the box, for example, click, and then drag a photo into it. For example, repeat this process on page 3 and 4. Click and drag the photo. Click and drag the photo. On page 5, fill in the information, name, the exoplanet, mass, radius, distance from star, etc. for the exoplanet that, in your opinion, could be a good candidate for a second Earth, and explain why. Because the report should be saved in PDF format, and the file name will consist of the first 3 letters of the country, the month, the day, and any 3 numbers from 000 to 999. For example, SPA, Spain, SPA, 05, May, 15, the day, 123.pdf. The report must be uploaded to the Google form specific. Finally, a NASE certificate of participation will be sent as soon as the report has been uploaded with the name of the teachers and participating students. Okay, thank you very much.
Thank you, Ricardo. I would like to be a little bit more concrete with this. The idea is that in the first information, in the intro, there are 3 activities, simple activities, very easy, that all the participants can do it. And after, they have to choose one favorite exoplanet. And there are 2 options. One is from one table, that this will be the presentation of Corina Toma. And after, the other possibility is from the report, the file with many exoplanets from NASA that will be presented, this contribution by Bresi Ocaña. Then the idea is that you choose what do you prefer. Probably for young children, for very small children, is better the table directly, and for older, then probably is better to choose directly for the repository. Then the idea now is that we have one contribution from Indonesia in order to present one of the activities that we have, okay, that we suggest that students prepare, okay. Then this Indonesia is a very strong project, a strong country in NASE, and this project, it is a good idea that they offer us, okay. Then I hope that Ronnie will be ready for it. And we have,
Rosa,
yeah,
at this moment, we cannot see the presentation. I suggest that the people present the contributions from their own countries and computers. If they have the presentations installed in their computers, probably it's better that each one present by their own the contributions, if you agree, because I believe that Ricardo has some problems with the
yes,
with the
yes.
transmission. Yeah.
Ronnie, do you have the last version of your PowerPoint?
Yes, I have the
Yes.
last version.
Could you
the
use that, please?
Yes,
Because
I
we
use
have difficulties with Ricardo, okay?
Mhm.
Okay, okay.
Great. Perfect. Go on.
Okay. So the share screen from the Ricardo. So it's okay.
Yeah,
Yes,
continue.
very good. Yes.
Okay.
Yeah,
No.
please continue. Yeah,
Okay.
yeah.
Hello everyone. Introduce myself. My name is Roni. I'm the amateur astronomer, and also I the astronomy communicator from Indonesia. Today, I would like to present you our project, the simulation of the spiral galaxy, which is a part of the Find Your Exoplanet program for the International Day of Light 2026. This project is collaboration between the several institutions in Indonesia, involving both the researchers and educators. Our main idea is very simple. Can we simulate something as complex as a galaxy using everyday materials? And surprisingly, the answer is yes. So, the spiral galaxy, yes, this slide. Before we go to the experiment, let's understand what is the spiral galaxy. So the galaxy have the different shapes. Based on the Hubble's classification, they can be spiral, bird spiral, or elliptical. Our home galaxy, the Milky Way, is a spiral galaxy. It has a central bulge and beautiful spiral arms and rotate around it. It is important to understand that this classification is not exactly an evolutionary sequence. However, physical processes such as gravitation, rotation, and interaction can explain how galaxies may change their shapes over time. And in this project, we try to recreate this structure using simple physics that we can observe directly. So the slide 3. The slide, okay, slide 3. This is the slide 3. Oh yeah. We use a glass filled with the water and add the small grain materials. And some example are fine sand, baking soda, or double set. Each material behaves differently. For example, salt dissolves too quickly, so it is not ideal for observation. For sand and baking soda work better because they remain visible in the water. With these simple materials, we can create patterns that look very similar to real galaxies. This makes the concept easier to understand, especially for the students. So, experiment steps and the results. We can look at how the experiments work step by step. The first is we steer the water in the glass quickly using a spoon, and this create a rotating motion in the water, similar to rotation in the galaxies. And then we stop stirring and add a spoonful of the material. Next, we wait and observe carefully. The particles slowly move and settle at the bottom. What we see is very interesting. The material forms a dense center, which represent the galactic bulge. Okay, maybe we can see in the before slide. So sorry, before slide number 3. And you can see in the figure 5. We can see in the center is the bulge, like the center of the galaxy, and at the same time, the spiral patterns appear around it, similar to spiral arms in a real galaxy. This simple experiment helps us to visualize how rotation and motion can create a large-scale structure.
Please, Ronnie, please, your slide. I don't see your slide.
Oh, okay. Okay.
You
I
stop sharing.
share.
Yes, share again. Okay.
Okay.
Okay, thank you.
Yep.
Great.
Okay. So, in this slide, after the spiral structure is formed, the system continues to evolve. As the motion of the water decreases, the structure becomes less organized, and the spiral arms slowly disappear, and the material spread out more evenly. In the end, the shape can become similar to an elliptical galaxy. So this demonstrates an important idea. Galaxies are not static objects. They can change over time due to the physical process. Even though our model is very simple, it gives a basic understanding of how galaxy evolution might be happen. So our project plan is we will collaborate with the high school students through the NASA workshop program, and students will actively participate in the experiment. They will perform the simulation, observe the result, and discuss what they see. And this hands-on activity is very important because it helps students learn science in interactive way. After that, we will document and report the result to the Find Your Exoplanet program as a part of the International Day of Light 2026 project. So the project will run from April until September 2026. So for the conclusion is the project showed that the complex astronomical phenomena can be explained using a simple experiment. By using water and small particles, we can simulate the structure and possible evolution of the galaxy. We hope this activity can inspire students to learn more about astronomy and science in general. I think this is my presentation. Thank you very much for your attention.
Thank you very much, Ronnie. I would like to invite to the floor if somebody have any questions. Comments, suggestions. If there are not comments.
I
We have time, and I would like to show you a video. Sorry, any question?
Can I ask something? Yes.
Yeah, of course.
Is there any simulation for an irregular type of galaxy that can be done easily?
Sorry?
No, for irregular, no.
No,
For
not
an
yet.
irregular.
No, remember.
But I suggest to all the participants that is an excellent homework for all of you.
No, yes. Remember, Margarita, that we are trying to represent something that is analogy. It's a bit complicated also because you continue moving the water and you pass from the spiral to elliptical galaxies, but we know that this is not the real process. It's not an evolutive process, the Hubble diagram. So we need to take care when we explain this is simulation, is not part of the evolution, the real evolution of galaxies. So the irregular galaxies follow another line of evolution. So it's a bit complicated in general.
And also the bar, the spiral bar, also it's not possible. But in any case,
galaxy, the Milky Way has a bar in the center. So the processes are very complex. This is just a way to show how the systems can evolve in the time in a particular state, but not is a general thing, and is not an evolutive process, the transformation from spiral to elliptical galaxies. So, well, we must take care.
I would like to mention that when you use a model, of course, there is one part that you can compare, but the rest in the model is not the reality, okay? Then should be careful in order to understand what is the part that we are interested to show. But in any case, I think it is a good idea, this example, because when the people don't understand very well that only for rotation can appear one spiral, okay? Because this is not so clear to imagine. And I think this is one opportunity, no more. If I can share with you the video that we have, I will try. It's only 1 minute video, and I think it could be a good idea. One moment, I have too much things here. Wow. Here. I hope that, will you see the video? Okay.
No,
it's very, very simple.
Yes, now yes, yeah.
You have this in the website of NASE, is in the workshop 11, and you can use different products. This is with bicarbonate. It is very easy. You can see, okay?
Very good.
This is another example. And the product, you can use different products. This is bicarbonate. You can use other things. Each one country have different products that is easy to find, and other so much difficult. Okay, then you decide and you choose and you take the best option. Well, the video is longer, but well, this is the nucleus. I think it is very interesting, this simulation. Okay? But well, I finish with the video, and I would like to invite the next speaker. In this case is Jibaji from Tanzania. He is a very active person in Tanzania, in Africa. I am very interested in one special activity that he is doing. I don't know, it is possible that Jibaji begin to talk now. I only would like to mention that he is working in translation NASE materials in Swahili. I think this is a very important thing because the official language in many countries in Africa is English, but really students and teachers use Swahili. And then this is very important group of activities that he's developing there. Jivaji, are you ready?
Ready. I hope that
Thank you.
you can see my
Yes.
screen, my
Yes.
presentation.
We can
Okay.
see.
So I'm Nore Jivaji. I'm an astronomer at the Open University of Tanzania and generally in Tanzania. And I'm also heading the Astronomy and Space Science Association of Tanzania and trying to do a lot of activities to develop and to get people interested in astronomy in Tanzania. So today we are interested in trying to understand the distances from solar system. When we talk of an exoplanet, our interest is not only in understanding that there are planets, but whether those planets can be similar to ours. So in order to understand whether they are similar to ours, we need to understand how far they are. So that's why we talk of distances from it, because stars produce extremely high energy. If something is very close, they will be very hot. If they're very far, then they will be very cold, and it has to be at the right distance. Now, energy, the intensity is related to the square of the inverse square of this. Means the farther away the object is, the intensity decreases by the square of the distance, which is extremely high. So when you double a distance, you get 4 times less energy. And you triple, you get almost 10 times less energy. So this is an important thing to understand about how distances will be, whether an exoplanet is something that is there is some place where it can be some place where it can be similar to our conditions, hopefully, because we are used to this type of considering the type of molecules and material that is found in the universe, carbon-based life is more likely, and water-based life. So we are interested in distances similar to ours. So we can understand distances under our conditions, how hot or cold our planets are. For example, Mercury is the closest to the sun, so it is very hot and similar to Venus. Mars is further away from us. It is a bit colder, and more distant planets like Uranus and Neptune are very cold. But Earth in particular has the right temperature for us to be able to live, for water to exist, and life to develop. Now, the distances to planets are not so easy to sort of understand theoretically, because it is the gravitational effects and the accumulation of material due to gravity. But there is an empirical law which can allow us to understand the distances from an empirical point of view, from a general point of view. Now, this is something that has been known for many years, hundreds of years, and roughly we say the distances are about, it's a geometric progression, means each planet is twice as far as the previous one. In mathematical form, it would be something like that. It's a bit complicated, but it's an empirical law. It's an empirical relationship, but it works for our solar system, and perhaps it might also be useful. Perhaps some other solar systems exoplanet systems may also be following that, but it's not a theoretical one. So it may work. It depends on the planet. But in order to understand our own solar system, we can use this what's called Bode's law, Titus-Bode's law, to make a model. Now, how to make a model depends on how far the objects are. And here in this case, you can see that I have put in all the planets from this. The sun is it begins with the sun. And the distance in AU are more easy. The distance in AU is the distance of Earth from the sun is 1, and the rest of the planets are in terms of our Earth distances. So the extremes are the sun as the origin, as the starting point, and the Kuiper belt. Kuiper belt is the farthest place where we can see still a lot of bodies. We are still discovering them. It's very far. We have not seen much of them, but Pluto, for example, is part of the Kuiper belt object. And that is like the farthest in our solar system that we can talk about as solar system objects. Now, when you look at distances, you can see if you start from the Kuiper belt, from the sun to the Kuiper belt is about 40 AU. Now, if you halve that, because that's what the Bode's law is saying, you get about 20 AU and you get to Uranus. So you can see that I've boxed them in red, those that are following the Bode's law. And almost all the planets are following Bode's law except 1 or 2, and that is an exception, but it is very interesting to be able to model using this. So Uranus is half the Kuiper belt distance, and then Saturn is half the Uranus distance. Jupiter is half the Saturn distance. Asteroid belt, where there is also, it is like a broken planet, I think, and one of the dwarf planets exist, their series in the asteroid belt is also half the Jupiter distance. Again, if you go half of that to asteroid belt, you get to Mars. And if you get to half of Mars, you get to Venus. Earth is again a bit of an exception. But then when you go to half of Mercury, you get, so half of Venus, you get to Mercury. So there is a nice way of understanding and modeling this so that you can really appreciate how far these things are. Here, I've just shown you a picture of a strip. If you take a strip of paper, starting with the sun on one end and the Kuiper belt on the other end, you can easily do the folding into half of a strip of paper, and you will get these type of distances. I'll demonstrate that just now. If you can allow me, I will stop sharing now and show you physically how these things are working. Okay, let me just see where I can stop sharing. Share, okay. Sorry. Stop share. Just 1 minute.
Ricardo, ¿puedes dejar de compartir para que comparta él?
Sharing. Okay, I've stopped sharing. If you can keep a view, now I can show you, for example, I have a strip here with one end marked the Kuiper belt and one end marked the sun. When I fold that in half, if I fold that in half, what I'll get is the position of Uranus. You can see here, I have the position of Uranus from that. Now, as I said before, the Neptune is a bit of an exception, but we can easily get the position of Neptune by folding from Kuiper belt to Uranus. You can see we are folding here, and we'll get of Neptune here. Neptune is between Kuiper belt and Uranus. So then, when we fold again our strip from the sun to Uranus, you will get Saturn from that. So Saturn distance is here, I've marked here again. This you can see Saturn there now in between Uranus and the sun. So if you fold into half the Saturn distance, I'm folding it here again, you'll get to Jupiter. From Saturn, you'll get to Jupiter. I've marked here now Jupiter also. I don't know if you can see, if you get a gallery view, a speaker view, you might see. So by doing this half by half, I was able to get to asteroid belt here. For example, this is the asteroid belt. You can see the asteroid belt also, half of Jupiter distance. And then again from that, from the asteroid belt, half of sun to asteroid belt gives you Mars. And then now from Mars onwards, I hope that you'll appreciate that the distances are now extremely tightly packed in the strip. So half of that will give you Venus, half of Mars will give you Venus, and half of Venus will give you Mercury. But again, Earth as an exception, a bit of an exception, but it's very close. It's in between in between Venus and Mars. So you can make a strip like this easily, and you'll appreciate that the habitable zone is extremely small. You can see it's actually compared to the whole solar system. I hope that we can appreciate this type of model for people to understand how big our solar system is and how small our area that we can have, we can live in is in our solar system. Thank you very much.
Thank you very much, Jivaji. We are very happy to be exactly in the good part of the solar system. We cannot organize this meeting. This is evident. Yeah. Okay, thank you very much. I don't know if there are any questions for Jivaji.
The issue is to make students to make these models, you see. When they make a model, I myself, I was extremely impressed that only a small part like this is habitable in a whole solar system like. And we say, Jupiter, we can see the planets, we can see Saturn, but then they are extremely far away. And how far away they are, you can appreciate them in a model like this.
Yes, I think it is a very, very nice model. It is not exactly correct with the numbers, but doesn't matter. The idea is essential, and this is good. Okay.
And yeah, they can make it a very easily with just a simple material. Yeah.
Yeah. This video is not yet in the website of NASE because, well, it is a new video that we prepared for the course of astronomy for kids. But in any case, I can show you the video. But I think that Jivaji explained very, very well. But we have timed them. It is only a couple of minutes. You know that our videos are always very, very short. And this is the video. Okay, I have to move this one. Well, you have here the sun, the Kuiper belt. Okay, and then the idea is to fold one. Uranus, I think.
Yeah.
And after you fold again, it is not precision, okay? It is only a simple way to situate approximately everything. Neptune. You divide again. Okay. Jupiter. You fall again. This is asteroids belt. You fall again. Mars. And you fall again. Okay. We have Venus. And in the middle, it is not necessary to fall because you control the middle more or less. Mercury and the Earth. Okay. You can do it with the students. It is very easy, very simple. And well, I repeat, it is not exactly the numbers, no precision, but really the Titus body is, well, only a ruler that it is practical, but we know that it is not exactly it's not possible to demonstrate from a scientific point of view. Okay, thank you very much, Jivaji. You are an excellent teacher. You show us how to fall each one, another one, another one. Thank you. Excellent presentation. Thank you very much. Then
Thank you.
I don't know if there are any questions for him. No questions? Okay, then the next speaker is Corina Toma. She's also a NASE member from many years and very important member of NASA in the way that he's working in many occasions in many different countries. And she will introduce us one example that how to choose one exoplanet that could be habitable in the list that we suggest to you. Okay, then Corina, when you want.
It's okay?
Yeah.
Okay. Not good morning, not good day. Yes, it depends on the country. I'm happy to be with you today. And my job today is very simple because all the explanations are in the files you can read on the site. But in my opinion, it's something very interesting today because we are looking after exoplanets, but many years ago, all astronomers were looking to stars and to put their names on the name of the star. But now you see here from 1992, it was the first exoplanet found, but near pulsar, and we want an exoplanet near a star like our sun. And from there, then you can see how many exoplanets there are confirmed, and there are many other candidates which are not so good for the life which we understand to be. We want to find the life with water, with like our life with we don't understand how to be in another kind of life, yes? And there are some criteria, of course, to consider one exoplanet good or not for a second Earth. First criteria is the host star, the central star in the system, which has to have a mass less than or equal to 1.6 times the mass of our sun, yes? We can impose also, we have to impose, no, we have to impose also another criteria for the exoplanet mass, which has to be less than 10 times the mass of our Earth. And of course, we are interested in the exoplanet radius because of it has to be special density, of course, and this radius is about is less than 2 times has to be less than 2 times our radius of the radius of our Earth. Why we are interested also for the mass of exoplanet, I forgot to say, because of the gravity, the value of the gravity to retain an atmosphere, to have on that exoplanet an atmosphere, of course. And the fourth criteria It's also very important, the habitability zone, because if the distance between the host star and the exoplanet is too small or too large, we cannot have a life there because of the temperature on that exoplanet. And you can see here the spectral the spectral types, but not all the sections of this. But in any case, for these temperatures, the habitability zone, the distance has to be between these values. And I can show you here which is the habitability zone in our galaxy, because also in our galaxy you saw how many exoplanets we have. And we can also find one of them to be like our planet. And these are the zone in green in which we can find some exoplanets. And I choose not only one exoplanet to explain to you, I choose these 4 exoplanets, K2. K2 is the name of the star, and this star, 2 from one star, 1 from another, and so on, in Aquarius constellation. And I made here a table with a mass of the exoplanet, and all of these are good. These values are good in our conditions. Also for radius, it's okay for all of them. The distance to the stars is another table. I made another table here. And for every kind of spectral type. And I found that also the distance are okay. I compare also the stellar mass with our imposed condition, and all of them are okay if we consider, we can consider that all of these exoplanets are good for life, but we have to check in the future this. And at least I found that the best exoplanet is TRAPPIST-1e till now. I don't know tomorrow which will be. And also a very good exoplanet, a very good choice is Proxima Centauri b, and from my group is this. If you have some questions, but I think it's very simple for teachers, for us, to explain with this kind of tables which of exoplanet is a good choice or which one is not. Thank you.
Thank you very much, Corina. I don't know if we have any questions from the floor.
I have one question.
Okay.
Corina, thank you very much for your excellent presentation. Can you show us the previous slide with the tables here? What I didn't understand is all these exoplanets K2, 72,
3 and so on.
so these are exoplanets that belong in different stars, in different
Yes.
zones. Yes.
Only first two are from
First
the
two.
same
Okay.
star.
Okay.
K272, but this
Okay.
is K23, but in the same constellation, yes?
Yes, 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 yes.
It's near one. It's like this, and the temperatures on the star is very near, yes? You see, there are stars from MOV, M3V, and so on. Not like our in G.
Thank you. Thank you.
Okay. And because of this temperature, the small temperature of the star, also the distance has to be smaller, yes? This distance in astronomical unit is only, it's 10 times smaller than our distance from our star. Okay? So,
I think it is good to explain to the students that where our solar system, it is one possibility, but there are other kind of possibilities, no, depending on the central star mainly, and then well, and also depending of our technology, we know more or less about this. All of this, it is necessary to explain to them because they will be the future astronomers and they will be the people that can discover more and more and learn more and more about the other exoplanets. And this is very, very important. Thank you very much, Corina. I don't know if we have other comments, questions, no more? Okay.
I cannot see hands raised.
Then, Beatriz?
No. I just mentioned that there is no more hands.
Okay. Well, then I would like to know if Bresi Ocaña is connected or not.
No, not yet.
Not yet, Beatriz.
No, probably if she has some problems, so go with the next speaker.
Okay. Then in this case, maybe I suggest to continue with the next one speaker. And when she contact with us, we continue with her, okay? The next speaker, this will be the participant from Mongolia, Solomon Reshin. He was at the beginning, I am sure. Solomon, are you there?
Yes, I am here.
Then, do you agree that you begin your presentation because the previous speaker is not yet here? Okay. And thank you very much. I would like to introduce a little bit Solomon. Solomon is a very active person in Mongolia. He works strongly in NASE, and she knows very well the desert of Gobi. I participated in one event that she organized there. She tried to plant several trees with us with the help of different astronomers and IAU members. And then I think it is an excellent speaker in order to talk about the difficult situation of life in this kind of deserts. Okay. Then when you want, could you share your PowerPoint? Or we
yes, I try to share, but it doesn't work. Can you share for me?
Yes, of course.
Okay.
Ricardo, could you share the PowerPoint of Solomon, or I do it? If you want, I can do it.
Voy a intentarlo.
Thank you.
Don't worry, I can do it myself.
Yeah. One thing, please,
Yeah.
Rosa. One thing, please.
Okay.
For the people in the room, can you indicate exactly your names in each
Okay.
place,
Well,
because we need the list of participants, and I can see, for example, people who is identify as Bismarck, for example. I don't know who is Bismarck, and we would need the complete name and surname if you can indicate it. Thank you.
Thank you very much. Okay, Solomon, this is the PowerPoint.
Oh, yeah, okay. Thank you so much for sharing for me. And I am
No
okay.
problem.
So
It's my pleasure. Don't worry.
hello everyone, and my name is Salman Renchin. I come from Mongolia, and I teach remote sensing and space science at the National University of Mongolia. So I have also lots of activities with NASE, and every year we organize courses for our school teachers and amateur astronomers, and they really like NASE's opportunity. Thank you for this, Rosa and other organizer and teachers. Today I will share our some activities, past and future, now present activities on Mars or another exoplanet activities. So please next. So as we know, there are lots of research activities has done on Mars as is there is life or not. So in Mongolia, our group and our amateur astronomers, can you go back, Rosa? I just wanted to talk about
the first one.
Yeah, no, this one. Yeah, just
okay. This is okay.
No, the
No.
previous one. The
Previous
one.
Yeah. I'm sorry, this is
no.
we had also exoplanet exoplanet activities, and we had also participated naming exoplanet, and we win such exoplanet name, which name is Mazala, and planet is Bambrush. So Rosa, can you
excuse me, Solomon, can you change the slide, Rosa? Because we are seeing the next one.
This
Stop.
one, yeah.
Stop there.
Stop. And I will say next, okay? So then we have experience to outreach activities. We did participated naming of exoplanet. It encouraged many people. So it is very good example for us and for activities. And so we did also group people also went to Gobi Desert to explore how to similar our desert Gobi with this Mars. So first we understand that the research is science, technology, and education in public outreach is useful. Next, please. So it is also one of our research findings. We made some similar Earth anyways, like Mars. So we took some Mongolian Gobi Desert and Tarsis bulge on Mars. So we compare it with two regions from Mars in Mongolia. So there is similarity to large domal uplifted areas. So these comparative studies, Mongolian Plateau and Tarsis from Mars, excellent opportunity for understanding surface manifestation of plume drawing process on terrestrial planets and how they interact with cryospheres. So this is also from international journal. There is I made, and our people also use data from perseverance from Mars rover, and it is a very downloadable, free downloadable area. So we compare it, it's quite the similarity there is. Next, please. So here also, Mongolian Gobi is one of 24 biggest deserts in the world, and we are extreme cold. Sometimes it's -45 winter time. It somehow is a little bit similarity in Mars or everything. It is very convenient place to comparison with Mars as on Earth, or it could be useful for Mars climate change or something like this. Next, please. So one of good activities is outreach activities. There is Mars V. This is citizen science and outreach activity involve more young people and inspires teenagers also choose career in science technology, and also university students, and also we also going to do lots of things through Mars V. Citizen science outreach activity, and also we still do many activities through to go Gobi Desert, and also introduce people similar Mars area, and also archaeoastronomy, astrotourism, and astroculture, and it is very good for young people and even for amateur astronomers. Next, please. So this is just short my talk, and I did actually 17 page, but Rosa said only 5, and I cut it many.
Well,
Thank you.
I would like to thank you to Solomon for her presentation. I have a question about, you mentioned that there are astrotourists in this region. It is not a problem for pollution or all of this if many people go to that? I don't know.
Astrotourism, it is one of a very good dark sky, dark area. And through astrotourism, we can develop protect night sky. Protect night sky, and also to do some astroecology activity, plant trees under dark sky and something. Then every year we had organized, still we organize it. And I think Rosa, you also was one of activities.
Yeah. No, I was one of the lucky person to do that, but I don't know. It is, well, it depends on the volume of the people, of course. No, well, I don't know if there are any questions from the floor. I think it is a very special site in the world, of course. What is the range of temperature? Oh, sorry. Any
One question.
Yeah.
I mean, just to understand, I mean, when we say we are comparing it with Mars, do you see features on the ground which might be comparable, or is it in terms of temperature?
Yeah, it is. Yes, good question. This for ground surface and the uplift area, and also, of course, temperature different, but we are coldest desert in the world. That's why a little bit similarity. Of course, difference, much more difference climate, but it's in the on Earth we are more than similar other places.
It's more like isolation, which.
Yeah, there is almost no people, and also no.
Okay, understood. No, not much living, not many living things there.
Yeah, that is desert area and also not infrastructure, and the climate is very harsh, winter cold, the summer reasonable.
Okay, thank you.
Okay, thank you.
Any other questions? No? Okay. Then the next speaker, do you know if, Beatriz, do you know if Blessy
No,
is here? Not yet?
no, Brice no, is not here yet. No,
Okay.
I am trying to contact her, but well, go
Okay,
on.
okay.
Go
Well,
forward.
then in this case, I don't know, but our participant from Argelia, Hichem Gouergouri,
Hello, can you hear
is
me?
here. Hichem, hello.
Hello, hi.
Nice to
Can
see
you
you
hear me well?
again.
Thank you so much, Rosa. Hello, everyone.
Okay, do you want to use your PowerPoint to share with us your
Let
PowerPoint?
me try sharing.
Okay.
Can you see it?
I would like to mention that our participant from Argelia, he will talk about the Sahara Desert, and of course, in some way is similar to the previous presentation, but I think it's not exactly the same. They have complementary in some way. Okay, thank you, Hichem.
All right, thank you so much, Rosa. Hello, everyone. I'm Hichem Gergouri from Algeria. I work as a researcher in the research unit in scientific mediation and culture here in Algeria as an astrophysicist. And I'm going to present for you this talk from the Sahara to exoplanets, life in extreme environments, where you will see some similarities between the Sahara, especially here in Algeria, and some sceneries you have seen from Mars and maybe some arts from exoplanets and so on. So when we talk about extreme life in exoplanets, we usually either think about science fiction like the Interstellar movie. I'm sure that most of you have seen it, where there are some example of exoplanets where tidal waves are strong. There is this icy planet, there is this desert one. And even Earth in Interstellar was hostile to humans, so it was in extreme life condition. Or if you are a scientist and you have seen the images from different Mars rovers, sorry, or the moon, or Venus, or moons like Enceladus, you have seen these sceneries where extreme life is really, well, it's not exactly life, but it's an example of how extreme could be. But if you look at these images, when I saw these images at first, I thought it was made by AI. Well, actually, they were real pictures from the Algerian Sahara, took by an American photographer. I will talk about him later. But what took me off is the person in the astronaut suits, which made them look really in space. When we imagine life on other planets, we often think of distant world, but some of the best analogs already exist on Earth. For example, in the Algerian Sahara. So this is Andrew Studer, and his friend was wearing this astronaut suit to make the sceneries look like they are on Mars. And he was like, yeah, this place really looks like Mars. And I have seen it, I have been there. So you can't find any sign of life if you are trying to look for it, but you can see it in different ways. So Algeria is the biggest country in Africa. Almost 80% or 85% from it is deserts, and just the northern part, which is not. And the desert in Algeria is so variated, you can't find the same sceneries everywhere. For example, this is some parts of the northern parts of the Sahara, which is called the Erg. You can find those dunes. You can find some places with oasis. And you can find these sceneries that looks like Mars, where there is rocks and dust everywhere, with no plants, no sign of lives, and even mountains that you can find in the extreme south or the southern parts of Algeria. And the similarities between these places is that life condition can be very extreme. And what I mean by this, temperature can exceed 50 degrees during the day and drop below 20 to 30 degrees at night. So the difference between night and day is so huge. There is little surface water, extreme dryness everywhere, strong UV radiation, and frequent sandstorms, places where people cannot live unless they are adapted to these conditions. But despite these extreme conditions, we can still find some different type of lives like animals and insects. So the example that everyone knows is the dromedary deserts camel. These animals can survive weeks without water. They can they have protected eyes with shields that protects them from against the sandstorms. They have thick skin that protects them against the UV radiation. Other examples are the silver ant that we find in the deserts, scorpions, and reptiles. Well, those we can see, but there is another form of life that we cannot observe directly, which is the microbial life. And when we talk about life on exoplanets, we usually focus on microbial life because it's likely much more common than any other complex life, because evolution might take millions of years to reach some advanced kind of life. There is this kind of bacteria, for example, that live inside the rocks to avoid the radiation and heat, and we can find it in the surfaces that are not facing the sun. So you can see these green things on the rock. They are signs of this bacteria. I'm not an astrobiologist or biologist, so I may pronunciate the names wrong. I just made some basic research about these kinds of creatures. Other can enter a dormant state in dry soil and reactivate when water appears. So this kind of life can live in soil. And if there is no water, they enter like a hibernated mode or dormant states. And they can stay like that for decades until water reappear again and they reactivate again. And there is also some other bacteria or microbes that we can find in salty environments. This is some good examples of creatures that can live in extreme conditions. And the most impressive one for me was this fish that I found live in the Sahara. I never expect that fish can find ways to survive in Sahara, especially that water in Sahara is never stable. So there is water that appears in places and disappear from other places. This is called the Sahara killifish, or I don't know how to pronounce it, the biological name, but it's named after the place that we found in, which is the Saura. So we find Saurensis in the name. This species has not been observed in the wild for about 20 years and was considered possibly extinct. So we thought that it's extinct because the places where we used to find them in had no water anymore. In June 2024, there has been a research that has been published in Nature. They said that they found a large population of this fish in isolated deserts wed. When they did work field, they found some places where this fish was hidden. This environment has intermittent water. It appears in some area and disappears in others. And this discovery shows that life can persist in hidden environments, even when we think it has disappeared. Besides that, I wanted to talk about a project that has been going on for a year or so, which is called Tel Atlas Aerospace Algeria, which is a base that is that will be made here in this place that's called Brizina. which is in the west of Algeria. It's a space, aerospace base where people can do research or train or education. It includes habitat modules, training simulations, space agriculture, and rover driving. So it's a place where people can go there and experience how life on Mars or any other exoplanet similar to Mars can be. Discovering exoplanets with extreme conditions, hot, dry, or highly irritated, is not a sign of lifeless. The Algerian Sahara shows that life can survive in conditions we once thought possible. Life may not always be visible, but it may still exist, waiting for the right conditions. The desert is not empty, it's a window into other worlds. And thank you.
Thank you very much, Hisham. Very interesting. All of us, we want to go to Sahara Desert.
Yeah.
Thank you.
I would welcome you to visit Algeria and the Sahara very soon.
Yes, yes, we will do it.
Yeah.
Really, you are very active in Algeria, organizing courses, I know. Well, I don't know if we have any questions from other participants.
May I ask?
Margarita, yes, you
Yes.
have the hand raised.
Thank you. No, I can't pronounce. Okay, for your excellent presentation, very impressive. Rosa, please make a workshop in Algeria there in Sahara. So my
If they
question,
want all of us to there.
Yes.
For me, it's easy because it's very
one
easy
thing,
to arrive.
one small thing, you will see the total solar eclipse next year.
Yeah, we are
Oh,
going to
well, it's a
organize
good
something like this.
opportunity to go.
Yes.
can come, okay. My question is, why the color is reddish? It's because there is oxide ferrum on the sand. What's the chemical composition and has this color?
So if you see these pictures, I think the colors has been modified for the aesthetic of the image, but usually sand is yellow. It's not red, and I guess this picture was taken close to the sunset, so it looks more reddish. However, the places that really look like Mars surface are not sand. I will show you.
But not the composition. The composition is the normal one we have on Earth.
Yes, it's the same. This one, for example, this one, it's rocks and just dust that we can find maybe everywhere on Earth. But since it's a big surface, you can see here there is no plants, there is no water, there is nothing, and it kind of look like some places in Mars because there is no apparent life here. But the images of the dunes are not really red.
Okay, and the oasis is also very nice. I don't know if the colors have been a little bit modified, but it's.
I don't know about this image, but there are actually some places like this. I have seen them. Yeah.
Okay, thank you very much.
You're welcome.
Thank you, Hisham. Thank you very much. It was a very beautiful presentation. And, let's go to Algeria.
Yeah, welcome.
And next one, we go to the other part of the world. And we have one presentation from Finland. And they talk about Letonia. It is absolutely different that the deserts that we know after the presentation, the two previous presentations, but always all of them are in this planet, okay? The next speaker is Pasi Nurmi. He is the NASE member in Finland. He is in Turku, is organizing courses there. And the presentation is prepared by Sakari Eko, who is also NASE member, and he's retired, but he's living in Turku also, but he has a house in Laponia. Then he knows very well the the kind of climate, the animals there, because he's an excellent photographer. And he worked during many years taking photos of special animals in this difficult environment. Then, Pasi, do you want to share?
Yeah, maybe you
Thank
can
you very
see the
much.
screen. Yeah.
Yes.
Yeah, so hello everybody.
Yes.
So I will give this talk on behalf of Sakari. And of course, if you have any questions, I will answer whatever is of your
But
interest.
Sakari is here also, I think.
Ah, Sakari is here also. Okay.
Then you can talk with him and you decide what is the correct answer. Okay. I would like to invite you to share the full screen.
Yeah, I know. Yeah, it's just I have two screens and it's always like this. So
because it's the small ones.
I know
We can
it always
see in
says
any
the wrong
case.
screen.
But the
so
photos
that's
are
wrong.
so beautiful that could be a good idea to have.
I think it's better to do like
Hello,
this.
Sakari. I know that you are there. Okay. Well, doesn't matter. Don't worry.
Oh, wait a minute. Put this.
Do you want that I try to share your presentation?
No, it's okay. It's just just I have just two screens and it always says the wrong screen
Too much
when I
speech
put
for
it to
you.
full screen. You know. So let's try once more. So if I do it like this, and then I will.
Well,
put
doesn't
it
matter.
full screen.
Okay, don't worry,
No,
don't worry.
It always puts it to the wrong screen.
Don't worry.
When
This is
it's
fine.
full screen.
Now we can see the, no, now no.
Yeah. Okay, maybe it's better that I just do it like in the previous time, so it's not like completely full. Okay. Yeah, and then I can maybe put
Don't
this.
worry. Continuous. Don't worry.
Yeah. So maybe you see now already quite okay. So this is the story of northern winter and life at limits. And this is actually from Lapland, and these photos are by Sakari. And maybe this image could be, if you can image that this could be maybe from Mars, polar regions, or maybe Europe. So we have this kind of environment already in our own solar system also, as you know. So one can say that the main challenges of winter in the north are of course cold, snow and ice, wind and drought. And in the fells that are kind of mountains that are polished by the ice age, the wind drives the needle-like snow crystals, grinding plants or buses reaching over the snow surface. The water is of course frozen, and ice crystals forming in the plant cells can kill the plants. The food is scarce, but the need for energy is great due to cold. So they need a lot of things to eat also. And the bird living in these harshest conditions, thus suited, for example, is the rock ptarmigan. So this is the bird, rock ptarmigan, in Latin Lacopus mutus, and in Finnish kiiruna. You can all try to pronounce it, kiiruna. It lives mostly on fells, only ascending to the birch line. So the birch is the highest growing tree in these regions. And when the snow in the fells is so thick, it covers the twigs. Ptarmigans are these winter plummies is white as snow, a perfect camouflage. I have looked countless snow-covered boulders with binoculars when seeking ptarmigans. And many times I have first detected the bird by its shadow on the snow. And the plumage is thick and so warm that the highly reflective white color is needed, not for the camouflage only, but to avoid heat stroke due to the strong radiation by the springtime sun that's also amplified by the reflective snow. And ptarmigan has natural snowshoes. Maybe you know this kind of snowshoes, so that people use, but it has these natural snowshoes that it has in the winter. Around the toes is this thick plumage. And to digest the poor food it can find in the winter, ptarmigan's small intestine grows several times longer in fall, so it changing during the winter, and to shorten again towards summer. But the food is mostly twigs and buds, so something you can see in the picture. Very limited food sources. And patches dug open by reindeer or wind helped these ptarmigans to find their food. So here you can see a reindeer lurking in the background. And winter nights itself are very cold, but the ptarmigan sleep in a warm and cozy self-made snow hole that it closes with snow. And in the hole, the ptarmigan is safe from predators too. And in the pictures you can see, for example, the temperature in outside of these snow caves, and then what is the temperature inside the snow. So it's much less. And in the morning, it ducks the other end of the hole open and begins the daily activities. Here you can see like the cartoon of the snow hole, and then this is the snow hole in the what you can observe in the field. And now we are in the summer, so the summer outfit is thinner and again a perfect camouflage, and the digestive organs have adapted to fresh food also. So this was shortly a story about this ptarmigan, and so please you can also any questions and we try to answer with Sakari for the questions. Okay.
Thank you. Thank you, Pasi. I would like to invite to Sakari that to use the camera, and we can see the connection, Sakari. Okay. Well, I don't know if we have any questions for this presentation.
Can I ask one question, please?
Yes, of course, Jivaji.
When we talk of adaptation on Earth, do we expect that maybe life on other planets or anywhere else might also be different depending on when we detect it? I mean, it may be changing somehow. Is there any? I wonder if adaptation to changes like seasonal changes can also be reflected in life, maybe in the way we are looking for life in exoplanets. I'm just wondering. Because they look very different, depending on when it's very cold and when it is in warmer times. The animals look very different.
Yeah, I think this is a very general question, and I think the life is adaptive everywhere it actually lives. So it's part of the thing why it is like it is. So it has adapted if it has time to adapt to the conditions, and that's why we have so many different kind of species on the Earth. So I think we have to expect the same when I can say that when we find life in other planets. So. And I think we will find something that's very, very different, maybe, but we will see. I mean, we are living very exciting times, as we know at this time. Yeah.
Yeah, definitely. Thank you.
Yes, I absolutely agree that the life is absolutely strong and adapt in very difficult situations. I remember that I read several years ago that archaeologists discovered cereals in one of the Egyptian tombs, and they plant and they grow up. I think it is absolutely incredible, no? Because after, I don't know, but 2,000, 3,000 years, the plant grow up. I don't know. It's absolutely, we have to learn a lot in this area. But well, in any case, we are in the way to learn a lot in this way.
I would have a remark on
please, Bruno.
On the appearance of life. So far in astronomy and the technology we have, we are looking for life markers rather than life itself. So we have to define what could be the markers of life. And this is a concern because we have only one example. So we are trying to find things that has worked for us, but maybe it won't work for other form of life. And as we said, life can take in many, many forms already on Earth, to so many spaces, so many different capabilities. But I am confident that we will find something, and we cannot be. I don't want to restart an endless debate. We cannot be the only ones in the universe. Thank you.
This is true. Yeah. And also we have, how do you say, a short mentality, because we think that life is only a strict part that we are using every day, no? But it is much more open in this planet, and also in other situations with a different environment, probably appears other kind of adaptation, okay? And this is also very, very special and open many possibilities, a lot of that. Okay, then thank you very much, Pasi. Thank you to our team in Finland, Pasi Sakari, all together. It was very interesting. And also I recommended you visit Lapland after Argelia or before, doesn't matter, or go to Mongolia also. In any case, it is very interesting, everything. But I would like to continue with our program. And the next speaker in this case is from Spain. Also is a different reality. It is about Rio Tinto, Mars on Earth. And the speaker is Fernando Ordóñez. He's a good colleague in my country. We worked together for many occasions and many years. And I would like to say that he is a special person because he's living not far away from Rio Tinto. And Rio Tinto, I think it is a unique place in the world because the situation, it is not a desert, not a very cold area. It is a different place with a very, very special situation. I prefer that Fernando talk about this. Fernando, could you share your PowerPoint?
Oh, yes. Okay. Thank you very much, Rosa. And hello, everyone. I thought you were going to pass the slides, but in any case, I can do it. Excuse me one moment, because I was not prepared to share. Oh, please. Compartir. Presentación. Okay, I think you are
Yes,
viewing the
we
presentation.
can see.
Okay, thank you. Well, I'm going then. Over the next few minutes, I'd like to introduce you to a truly unique place in southern Spain. It's a location that blends thousands of years of history and culture with science, specifically the search for life on Mars. More recently, it has also become a hub for scientific tourism, showcasing its potential as one of the world's premier Mars analogs. This place is called Rio Tinto, as Rosa said, which literally means Red River in Spanish. As you can see in this first picture, the name is incredibly fitting, well-fitting, as the waters in there have a deep, vibrant red hue. And the next slide, so excuse me. Okay. This area is located in the so-called Iberian Pyrite Belt, stretching across Spain and Portugal, as you can see in these maps. This belt is one of the largest deposits of metallic sulfides on Earth, formed over 350 million years ago by volcanic activity. As you can see in this map, also the nearby village of Rio Tinto takes its name from the river itself. This, you can see one of the biggest mines. Mining here dates back to at least the 8th century BC, though it was the Romans who exploited it most intensively. While pyrite is ferrous sulfide, iron sulfide, the region is also rich in gold, silver, copper, tin, and lead. And mining activity continues until today, to this day. The iron in pyrite is typically in a reduced state, iron 2. However, the region also contains these other oxidized minerals like jarosite and hematite. These minerals transforms the landscape into a palette of reds, ochres, oranges, and yellows all over the area, all over the zone. And what is truly remarkable. Science has recently proven that these oxidized minerals are not just a product of geology, but of biology. Microorganisms living in the subsurface actually transform these minerals through their metabolism. This became a global sensation when these exact same materials were discovered on Mars. It raises then a thrilling question. Could Martian jarosite and hematite also be the byproduct of ancient life, just like here at Rio Tinto? Well, Rio Tinto, Red River, is essentially a laboratory, a 100-kilometer long natural laboratory flowing through the province from north to south through the province of Huelva, from the mountains, from the Pyrite Belt to the Atlantic Ocean. Well, you can see the red colors in the water, and to the untrained eye, this river appears to harbor no life at all. It's highly acidic, pH 2.3, all over the way, and is saturated, has a high concentration of dissolved iron that gives the waters, sediments, and even riverbanks their characteristic red color. And when you go down, as you go deeper to the sediments, oxygen levels drop to 0. So at first glance, it seems impossible for developed life to exist here. In fact, no fish, no frogs, no amphibians, no birds. For a long time, people thought Rio Tinto was a dead river. It's like a victim of mining pollution. But we were wrong. As it has been shown by 35 years of research in the Madrid Astrobiology Center in association with NASA, this river is teeming with life, other kind of life. The stars of this ecosystem are extremophiles. It's an amazing bacteria that don't just survive in these extreme conditions, they thrive in them. They survive, they feed, they grow here. In fact, these bacteria are the ones creating these conditions, not the mining. They break down minerals underground, oxidizing the iron and turning also sulfides into sulfuric acid, which is responsible for the low pH in the river. These bacteria have been shaping this landscape for millions of years, and they're responsible for the presence here of jarosite and hematite. So it's incredible news. Well, we know now that life can exist deep underground without an atmosphere, covered by tons and tons, hundreds of meters of sulfide rock, and producing minerals similar to those found recently on Mars. If this happens on Earth, could life on Mars have followed a similar path? Could we find traces of similar bacteria in the Martian subsurface? This is why Rio Tinto is now considered one of the best Mars analogs on the planet. Now, space agency like European Space Agency or NASA, interested in the search for life beyond Earth, are not only studying the extremophiles present in Rio Tinto, but are also using this area in 2 or 3 various research projects in which, as you can see, equipment and devices that will later be used in the exploration of Mars are tests specifically designed for the detection of life on the red planet. And finally, I would like to tell you that today, Rio Tinto is not just a site for world-class research. It's an educational and even tourist landmark. It's a place where students, scientists, and travelers can visit a spectacular piece of Mars right here in southern Spain. That's all. Thank you very much.
Fernando, I don't know if we have any questions from the floor.
I have one, Rosa.
Yeah.
I would like to know your opinion about why we didn't find life on Mars until now. We need better technology, or we need people doing the experiments on Mars?
Well, if life in Mars has to be like the one detected in Rio Tinto, probably it is not a few centimeters from surface. We need to go deeper. This is a problem with today technology. Probably we need not only scratch in the surface, but go at these bacteria have been found oxidizing iron in Rio Tinto at by drilling at 500 meters deep. So maybe the life in Mars is well down the surface.
Yes, it's good to say that because the people believe that we will find very easy life on the surface, and we need to do a very hard job to find
Yes.
it.
Yes, I think so.
I believe that probably we cannot say that the simple sentence, don't exist life in Mars. I think it's much more correct to say we cannot find life in Mars because it's not exactly the same. Don't exist and don't find. Well, I don't know if there are any questions more for Fernando.
Maybe
Yes,
Ronnie Sriamara.
Yes. Nice presentation, Mr. Fernando.
Thank you.
I want to ask you about your research. How deep to explore the material on the Mars? 1 meter is enough to get the sample.
So sorry, I'm not sure if I understood you.
How deep to get the sample? The sample from the land of the Mars.
Yes. Yeah. I think it's a problem for technology to drill deep, very deep in Mars without astronauts doing the job there. If we rely on robotic machines, it's very difficult because here in Rio Tinto, the drilling has gone so far to 600 meters down the surface. It's very difficult to do that in Mars so far.
Okay. So this is the minimum, the minimum dip.
No, I don't know if the minimum, but the experiments in Rio Tinto have drilled a long quantity of terrain.
Okay, thank you.
Yeah, my question is whether this life that you have in Rio Tinto, is it carbon based or is it like minerals which are duplicating? I don't know what do we mean by life there, because we are talking of mineral based life. Is it carbon like hydrocarbons based life?
No. They literally, these bacteria eat rock. They obtain the energy from a chemical reaction, oxidizing the ferrous iron 2 to iron 3, and oxidizing also sulfide to sulfates. From sulfide to sulfates, and from ferrous to ferric ion. And that's how they obtain the energy. They don't need sunlight. They don't need oxygen. and they are extremophiles, rich acidophiles.
I wonder whether the material from it, because we are saying our bodies, our proteins, and everything are made from hydrocarbons. So
Oh, yes, but this also, of course, these bacteria are made from hydrocarbons. They have a special, of course, they are not metallic bacteria.
Yeah, that's what I.
But they have special properties in its body to preserve the nucleus and the material of this body to preserve from these acidic surroundings.
Right, I understand. Thank you. So still the carbon-based research is the right one, isn't it? I mean, when we say the universe, we say carbon and water are universal. So we still expected life to be carbon-based, hydrocarbon-based.
Yes, I agree. Life is, as we know, is carbon-based, but the food can be a lot of different things.
Margarita?
Thank you very much for this very, very interesting presentation. I would like to ask Fernando, these extremophiles can be found all over Rio Tinto and up to 600 meters down. That means, do they have any preference on living in special parts, or it's just where food is?
I'm afraid I cannot answer your question. I can only I know these research projects to a level, and I cannot answer your question. But I could if I can be in contact with you later, I could give you some studies about this thing.
And another question is, they formulate communities and they are networking.
Well, these bacteria can be found alone, sometimes in pairs or in groups. And it's true that they're in the water, but also in the sediments and in the rock down under.
And they cooperate or between them?
Between them, I don't know. I don't know so sorry.
No, thank you very much. Okay.
Well, I think it is a very special place, Rio Tinto. And I remember when I visit there are some vegetables, some plants that they are living in a awful soil with a lot of metals, heavy metals, and it was living there. Then the adaptation of life to a terrible place is also possible. Not only these bacteria, no, it is normal plants, no, because there are some specific plants, but there were. And also, I remember that somebody mentioned that the color of the river changed if they go, will be in 1 or 2 days raining, and then the color change. Could you explain a little bit, Fernando, about this, if you know?
Now, well, first of all, you're right. Even in the rocks, over the rocks which are covered by water, you can find biofilms of algae. I don't know in English, algae. So it's incredible that some kind of life could survive in pH like 2 or 3. And the change of colors in the waters, I think, is only a matter of dilution, maybe with rainwater.
No.
And changes in
the guide
pH also, no?
The guide in Rio Tinto explained that there are one kind of bacteria, I don't know, inside the river that when they produce an acid environment, they produce the acid themselves, okay?
Yes.
When nobody knows the reason, but when the meteorology say to us that in a couple of days will be a lot of rain, of course, with the water, decrease the acidity. Then, what is the solution for bacteria? Then they begin to produce more and more and more acid before then the color of the river changes, is more red, in order to obtain a good acidity and survive after it was raining. Okay, well, it was the person professional guide in Rio Tinto that explained us. He said that the people living there knows that the color of the river informed about the future of meteorology. They knows because the normal people knows that. And they try to discover the reason. They discovered and changed the pH, but they don't know how the bacteria knows that could be necessary to produce more acidity. It was absolutely a very special place. I recommended you that visit also after Argelia and after Gobi and after to go to Lapland, you have to go to Rio Tinto, okay?
Well, many times the people from villages nearby are clever than the scientists, know the nature around them very well. But the red color is for iron, not really not pH, but iron. The presence of iron 3 is the reason for the red color. I don't think the concentration of iron can change so quickly, and I think it's a matter of dilution maybe, but anyway, we'll have to ask to the people from the village, to grandparents and grandmothers from there.
The guide explained us this situation. It was very surprising. Well, in any case, I don't know if you have more questions. If you want, I have one video of Rio Tinto that we can see. I think it is short. It is a video that Ricardo prepared when he visited. Oh, one moment. What is that? Oh, I lost my video here. Okay. We visit Ricardo and a group of people decide together, but Ricardo took the video, Rosano. This is the color of the river. Is red wine, okay? Not only red wine. It is a very intensive red color. You can visit with a train that we saw in one of the slides of Fernando. And this is the color of the river, absolutely impressive. You can see here with more detail. There are some plants, not a lot of them, but some cases, small plants that survive. Okay, this is all. Well,
yeah, thank you. Yeah,
you have to visit Rio Tinto. Okay. Well, let's go. If you don't have any questions,
you are all invited to come here. I'll be very glad to be with you.
Oh, be careful, because he's living very close to Rio Tinto, and this is dangerous for you to invite us. Thank you, Fernando. We enjoy very much to know more about Rio Tinto. Well, the next speaker is Alejandro Sarabia from Honduras. that sorry. Alejandro, are you here?
Hello, everyone. Yes, I'm here.
Ah.
Can you hear me?
Okay. Hello.
Yep. Hello.
Welcome.
Thank you.
Well, we are writing your presentation.
Awesome. Just a few seconds. I'm just going to share my screen.
Okay, then I have time to say that Honduras is in NASE from the beginning of the beginning of the beginning. I don't know how many years ago. And they are working in cooperation with the Ministry of Education, and they are organizing many courses of NASE there. The chair in this moment is Ricardo Pastrana, regards to him. And also Alejandro is one member of the big team, because it's a very big team in this country. Thank you, Alejandro, when you want.
Thank you. Thank you very much. Yes, indeed. We are, I think, a nice team here in Honduras, and we also collaborate with people around in the region, Guatemala and other places in Central America. So thank you for the invitation. Thank you for the nice talk that Fernando gave. Quite a remarkable place. And I think that brings us back to Mars, indeed. I don't think I have to try too much to convince you that Mars isn't a place where you want to go on a beach vacation. It's quite a nice, unless you are an extremophile. But it is a very dry place, and you can see it from the picture here. It actually looks like a big desert, and as you can see in this other picture taken from a rover, every time I show this to my students, it's like, oh my, it's like they are very surprised because it looks like a desert on Earth. And indeed, right, because we're in the same planetary system, it is not a surprise that Mars is actually very much in some regards like our own planet. And you don't see a lot of humidity there. When you try to measure the amount of water in the atmosphere, is also a very tiny amount, because Mars doesn't really have a big atmosphere, as you know. And however, is there any evidence for water on Mars, or any fissure in the geology or in the topography that we can actually say there must have been something flowing here? And the answer to the question is yes. And you see this kind of fissure you see here, and the color is the the altitude of the place, these places being the highest, and the blue here is being the lowest places. And you can see, you can very clearly see on this image that there must have been something flowing on the surface of Mars. And you can actually do a little bit more than that, better than that, and actually calculate how much of a fluid you had when all these features were made, and you get something like this. This is a quick calculation that I made, and you get these numbers. When you compare it to other places like on Earth, calculation for glaciers, you actually get pretty similar numbers. And what I mean by if you want to actually see the places, for example, this is in North America, and you see places like here on the state of Washington, you see similar features in all these areas here. And where are they coming from? Well, geologists believe that this is coming from big flooding events from the glaciers, when they were, you form like dams of ice in this part of the region, and then you have this accumulation of water, and as the temperature of the planet were rising, then the dams broke, and then you see all these floodings, and they left basically no soil in this area. That's why it's very arid. And you can see some similar features on Mars. Let me go back to my presentations. And if you want to get a better idea of how much water or so much fluid you had flowing in this area, and you can actually see that this is coming from the highest places to the lowest places. And this, you get a number of these, which is a tiny amount, but the Mississippi River, which is one of the major rivers in North America. But if you kind of see kind of similar numbers to the lower limit of this calculation. So there was a lot of fluid going or flowing in this area. Where on Mars is this particular area, you see that it is over here. Right here, you see this very interesting feature, but it's not alone, it's not isolated. You see all these similar features all along this, what you can actually match or imagine that, or convince yourself that is probably some coastlines. And you see all this feature here of probably a fluid going from the highest places to the lower places. And some people thought that already, and they actually made a map of elevations. Not only that, you also see in all these high places, you see a lot of craters, and you can also, you know, talk to geologists and convince yourself that this is probably the oldest surface on the planet. Well, in this area, you don't see anything. You basically see no crater, just a little features here and there, but nothing compared to what you see in the highest places. And how can you have that in a planet, right? And how can, if you compare it to Earth, you kind of see similar features where you have no sign of any craters at all, and that is why. And why is that? Because we have erosion, and we have oceans, and we have the wind that are eroding the features in the topography. Something similar might have happened here on Mars, where you see nothing here because there was some erosion. This is probably the newest surface, because this is old, full with craters, and you see nothing here. So some people have already thought of this, and they actually made a map of how a coastline in the northern hemisphere on Mars must have looked like, with a big sea in the North Pole of, around the North Pole. You see the cap here, the polar cap, and this is all the area where you actually see no crater structures compared to the other places. So the big question here is, where is that Mars? Have we seen that? Where is that water or that fluid? Because we now see a big desert. And have we seen anything in the present that, you know, gives us hints that there must have been some water on Mars? And the question to that, the answer to that question is yes. Actually, we have seen when you this is the Phoenix lander, and you scrape a little bit of the surface on Mars, and you actually saw ice on the subsurface of Mars. And then you ask yourself, well, if you have evidence in the topography, if you have actually seen iced water, or water, you know, ice in the form of water in the subsurface of Mars, where all the water went? And the answer to that question is related to the atmosphere of Mars, and how water, or how matter behaves at different temperature, the combination of temperature and pressure. And you see here, this is a phase diagram, but don't worry, we have a cool experiment that we'll do to demonstrate this. And you see that it in order to have liquid water, you have to be in this kind of sweet area where you have the right temperature and the right pressure. And so if you have the same pressure but different temperature, you will be in the gas area or solid area. And the same, if you have the same temperature but you have lower pressure, you will be in the gas phase. And this is for all the potential fluids that could have been on Mars. This is for water. This is for CO, because we know that the caps are made of a mixture of ice of ice water and CO, ice of CO. So what happened to the atmosphere of Mars? There are many possibilities, but this is probably the most likely, where the solar wind eroded the atmosphere of Mars, and these sputtering events where you slowly just erode and kind of blow away the surface, the atmosphere of Mars, because Mars, as you know, is smaller than Earth, and it has just less gravity to hold on the gas component of the planet, which is the atmosphere. So it's very likely that you have this erosion in the atmosphere of Mars. And this is where the cool part comes in. And I just gonna ask you to wait for me just a few seconds where I get my boiling water. I'm going to explain first the experiment, and this is something very nice that you can do with the students. Is if you have a pot of water, hot, it has to be hot, probably 80 Celsius. And the idea is that you will get this water inside, and then you will lower the pressure inside the syringe, and you will have the water boiling even when it is below 100 degrees. So just hold on for a second. I'll be right back. It will be just a fraction of a second. I'll be back. Oops. Be back. Okay, I'm back. And this is where you get the syringe. I think I have to just a second.
Estás muteada, Rosa.
Thank you. Okay.
Yes, where are you? You want to say something? Okay, here's my water. Let me show you what I have here. And the idea is, as you can see, there's steam coming out of here. And let me see if I can do this. I've done it. The water is around just actually have a thermometer here. You might not be able to see it, but it is coming up, coming up, coming up. You might not be able to see it, but it's probably around 70 something, 80 Celsius, somewhere around here. And then the cool part is where you make it boil. Let me just, you see the water, the temperature of the water. And actually you can see it, you can see it boiling even right now. Just let me go back to the experiment. And you can see it is actually boiling right now.
Yeah.
Oops. Oh my goodness, where's water is boiling.
Yeah.
Oops. And you have to kind of I hope you're seeing the water boiling inside the syringe.
Yeah.
So it is a very cool experiment that you can do with your students. And I think that is all from me. And just thank you for
Excellent.
letting
Thank
me
you
be
very
part of
much.
this. Thank you.
Thank you,
This-
Alejandro.
You're welcome.
I hope that you will have some questions for you. No questions?
No, I cannot see raises hands.
Well, okay. Then I enjoy very much your experiment with us, because a lot of people here probably don't ask because we use this experiment in NASA.
Yes.
But in any case, I think it is very beautiful that you are doing it in life with us together.
Can I ask one question?
This is the best. Thank you.
Rosa, one question, please.
Yeah.
What
Jivaji.
kind of timeline? What kind of timeline do we have here? I mean, in terms of how far into the formation of Mars did the water exist, and now, after how long would it have gone away? Means, was there atmosphere sufficient pressure at one time? And what timeline do you think in the formation of the planet would this have happened?
That's a great question. I'm not sure about the answer, and I think one way to do that is first the crater surface, and what you do is you kind of have to compare it to other features in other solar system bodies. And I think what they have done is they have dated the craters comparing to the moon, and I think they separate the geological. I'm not a geologist, and but they separate the geological eras. I think the last one is the Noachian, then you have the Hesperian or something like that, and probably all these crater features are coming from. I had a plot with that actually that I can show you, but it will take me a little bit.
Well,
But I think it is in the order.
Yeah.
It is.
Yes,
Just a second. Just a second. Just a second. I'm sorry, I'm taking so much time.
Bruno is ready to ask something.
Yes. There you go. So you see.
Okay.
Oh, go ahead. If you go ahead, because I clearly don't know the answer to this.
Okay, all these phenomena concerning the water on the surface of Mars, is it related to the loss of the magnetic field of Mars during its formation?
I believe. Can you hear me? Yes. I believe so. Mars isn't geologically alive, right? It doesn't have a hot nucleus, and you don't have a magnetic field, so you cannot protect yourself from the solar wind, and that must have caused the erosion of the atmosphere. There is evidence for that, and I had another plot that I can show you. But I wanted to point out that the way they date these geological features on Mars is by comparison to the moon. And they kind of date craters by comparison, and they have separated the areas by Noachian, Hesperian, Amazonian, and Amazonian is the newest surface, and there is around probably 3 billion years. So you kind of get an estimate of where must have been something flowing on the surface. It must have been a long time ago, in the order of a few billions of years. Do we know this, for sure? Maybe not. But this is a kind of a guesstimate by comparison to the moon. And we know that there must have been some erosion on the surface of Mars, because when you compare the abundances, there is another cool plot here that I want to show. Wait, when you compare the abundances of argon, in this particular, there is also argon 40, but that's like 1,000 times more abundant. When you compare these two isotopes, you compare the sun. If this is argon is very unlikely to react and to change because of the chemistry. When you compare it to the abundances in the sun, Jupiter, even on Earth, you see that they are kind of the same amount of abundances. But then when you compare it to Mars, and all these are measurements from different pros, but you see the arrow bars here being very big. But you get it from these actual measurement in the surface, and you get very different amounts. So something must have happened to the atmosphere of Mars, erosion, because you do not see the same abundances. And this is kind of probably some more in detail evidence of something happening to the atmosphere of Mars. So yes, why that happened? Probably what you were saying, the combination of having just not enough mass and not being geologically alive, that you can hold on on your atmosphere, and also you cannot protect yourself with the magnetic field.
Great. A lot of information to chew. I think a lot of new things here we have seen today. Thank you.
Sure, you're welcome.
Rosa, estás muteada.
Sorry, thank you. I don't know if Bruno have a question that Beatriz said before. No? Okay. Thank you
Was
very
a
much,
comment,
Alejandro.
yeah.
We enjoy very much your presentation. And I am especially very happy because you are doing the activity with us. Okay,
Thank you.
Well, the next speaker is Margarita Metaxa from Greece. She's one of the important members in NASE, of course. And I would like to invite her to show us the PowerPoint and to explain the presentation to us.
Yes. So have a good day also from me, from Athens. It's a great honor to be part of this program. Thank you, Rosa. Thank you, Beatrice. So today we started a journey where science meets inspiration and perspective based on the antiquity question, are we alone? Today, anymore, due to the rapid technological progress, mainly the last 35 years, this question is not anymore philosophical. It's mainly scientific. This question, of course, is related to the core questions. How does life begin on Earth? Does life exist also elsewhere than Earth? And how can we find life in the universe? These are the main questions that are the questions that astrobiology addresses, and astrobiology is an extremely interdisciplinary scientific field, as we all understood from this presentation. Of course, behind this question, the main question is, what is life? And hearing Fernando and seeing all these extreme places on Earth, we can say that there isn't a specific definition for life that could match what life is, or in other words, we could say that maybe life can't be confined only in one sentence. In order to understand a little bit more about life and the way that came up on Earth or in the universe, we will follow the scale of the time to see what came, how it came and emerged on Earth. And we will start, of course, from Earth. And why not to start from Earth and start from Mars, let's say, or Venus? This wouldn't change the way that we're going to search. So, from the cosmic calendar, it was a very genius idea by Sagan. He compressed all the entire history of the universe into a single year, where 1 second was 500 years and 1 month about more than 1 billion years. So on the 1st of January, the Big Bang happened. On the 15th of March, our galaxy was created, and on the 31st of August, our sun and solar system was formed. The planets were formed through collisions with smaller bodies, and this is very important to know. Smaller bodies also collide with Mars, as Fernando said, collide with Moon and probably other inner planets. On Earth, then volcanic activity started, and this volcanic activity created a primitive atmosphere rich in carbon dioxide water vapors, and nitrogen. As Earth cooled down, oceans formed. Of course, the oceans were not from water, as we know. They had the main composition was, as I told you, from the other elements. And in these primordial soups, in these oceans, appeared organic molecules. And eventually from them, the first cells appeared. On the 21st of September, the first photosynthesis appeared from the phytoplankton, which released finally oxygen, leading the great oxidation event, a turning point that made the complex life possible on Earth. On the 31st of December, the first human, late at night, around 10 o'clock at night, appeared, and in the final seconds of the year, all recorded human history has been written. So it seems that on Earth, life appeared quite quickly, and when it appeared, it thrived. All previous presentations that we heard today made obvious that life needs essential ingredients go through. But how these organic molecules, as Fernando said, and through the comment of Juicy, how these organic molecules and water reached Earth. Possibly the answer lies in minor bodies that have heavy bombarded Earth and other planets. So we have to look also in asteroids, like in Bennu. In Bennu, we found amino acids and organic components, as well in various comets and meteorites. So now we can also go and search, as we have already heard, on the planets of our solar system, for instance, Mars or Venus. And why not to mention K2-18b, as Corina told us in her presentation. And in this exoplanet, K2-18b, some very, very interesting data came up after observing this solar system. We saw that on the atmosphere of this exoplanet, we found methane, carbon dioxide, and dimethyl sulfide. This DMS that is an organic biosignature that maybe life exists, and I'm saying that because dimethyl sulfide, on Earth at least, occurs only when we have life activity. Of course, as just to clarify things, these are only some indications. We cannot rely on this to say that we have found life elsewhere than Earth. More research has to go through on it. But yes, K2-18b is a very interesting example of a candidate of life. And this also made us to think that there are also some other worlds that nowadays are called Haitian, and probably on these worlds life can be found. We look also in moons of other planets like Europa and Enceladus and Titan, where more or less environments like those that in Spain that was presented can be found. And of course, subsurface oceans beneath the ice of these moons is a fact that they exist, and maybe there are some also microbes can be found in future missions. So we have a lot of challenges when we are going to see if there is life in places beyond Earth. The challenges is the vast distance. For instance, it took us about 7 years to reach Saturn with the Cassini missions, or 9 years to reach Pluto with the New Horizon missions. This distance means, of course, extremely high cost and extreme technological limits and conditions, since the temperatures are very low or very high, the atmospheres are very toxic, and the radiation is in a very high level. And the way to identify and analyze the chemical composition of this faraway object is either with direct detection, that means we use satellites and robots like Perseverance and Huygens on Titan, or indirect detection using spectroscopy with the space telescopes. And just to show you a way that spectroscopy is being done for the search of life, we, with this space telescope, analyze light from the star. And then when the exoplanet passes in front of the star, we take again the light, which is analyzed, and there we can find absorption lines. And abstracting these two spectra, we can identify the chemical composition of the atmosphere of the exoplanet. So, with a very careful detection, we can find, for instance, water or methane. But overall, it seems that we have found the main components of life in our solar system. We can find it also in interstellar material, more or less all over our universe, let's say. So maybe the central question behind what is life is, why do the fundamental constants we have in our universe, that is gravitational constant or the electron charge and about 20 more, have the values they do, making possible this universe, the universe we live for life? This is a very interesting and central question to be answered. But it seems, as we have started this morning, this journey of searching life continues. And the main motto of the Star Trek, to explore strange new worlds, to seek out new life and new civilizations, to boldly go where no man has gone before, is to be continued and is thought to be very interesting and learn what is going to be. Thank you.
Wonderful. Thank you very much.
Thank you very much for your contribution. I would like to ask if we have any questions from the floor.
The problem is that I can't see you now. Why?
Oh, I don't know.
I have
Maybe
to
if
stop
you
sharing.
finish to share.
Stop sharing.
Okay, now I can see.
Now.
Okay.
Okay. Maybe we have some questions, comments about the presentation. I would like to say to you, congratulations for the video. It was absolutely impressive. Very beautiful. Any questions? No?
I cannot see any hand
Yeah,
raised.
maybe if I can ask one question here.
Yeah.
How much work is being done? I mean, I don't know, in terms of research, for example, quantum nature, in terms of electronics and all that. So much work we see in the news, but hardly we see any news about search for life. I wonder how much people are paying attention to, or how much work can be done or is being done. It's a useful question to understand whether we are really trying hard enough to ask the question and to get the answers. Just a general comment. We don't see too much news in the news. I read a lot of new discoveries and all that, but we don't see too much about it.
Last year were quite a lot of news about the K2-18b, let's say, exoplanet with finding the atmosphere. Probably this year we have not yet some data on this field, but I'm sure that I know that this is the main one of the main research questions that they are trying to be answered, and in astronomy and in biology, in astrobiology. Okay, it's maybe the central question of our century, the 21st.
Yeah. Remember that we have now some telescopes devoted to search for atmospheres, like the Vera Rubin, and of course the Webb, the James Webb telescope. But the James Webb is orbiting the sun, so we need a full year to cover all the celestial sphere. So we need time to produce data about the atmosphere, the atmospheres in general from exoplanets. So our limit is the technology, I think, right now, and the time. That is another problem. We need time to take that data.
But they are working on that field since the first exoplanet was discovered.
Yeah.
It's more or less about 30 or 35 years. And many things have come up by enhancing technology. That means the space telescopes, okay? That can identify and can analyze anymore even the atmospheres of exoplanets, as I show you. So this is something very an advancement that we couldn't have thought of it some years ago. And I'm sure that much more are going to happen that now we can't realize.
Yeah. Bruno?
Yeah. To get back to the core of Dr. Givagi's question about why don't we have such information in the news, I just say, unfortunately, there is currently a lot more information about our capacity of destroying life on Earth. And fortunately for us, this gives us a lot of room to progress. And we have to persevere in our science, in our outreach, and our understanding of the world. It's just a remark like this. So keep on going, keep on working, keep on having hope in humankind, because it's not easy to keep hope in humankind currently. And science can help us keep the line. Okay, so persevere.
Thank you, Bruno.
Well, thank you very much. Thank you, Greta. And I would like to finish with the last presentation.
Prissy is entering. Rosa, she had a bad time, I think, and I will try to share with her the link, because she lost the Zoom link. I don't know why.
Okay. The last presentation is about the NASA exoplanet catalog that we mentioned that for participating in this project, there are two possibilities. One is to take one exoplanet in the list that we offer to all the participants, but the other one is to go directly to the exoplanet catalog. Okay, and the next speaker is Bresi Ocaña, that we hope that he contact with us now.
Give me a moment. I will try to.
Okay. She had several problems for connection.
Let's see.
finally we can contact her.
I just sent the link. Let's see if she can enter.
The idea is that students find one possible candidate to be a habitable exoplanet. And of course, it is necessary to explain to them that, well, they can see that it's not so easy. But well, in any case, it is a good way in order to know the characteristics that we need that could be possible to obtain to find this exoplanet, and they can see that really is not so easy.
Well, I don't know what is happening. Well, in any case, Rosa, if you want, and while Breezy is try to enter, I can show very soon the NASA website for exoplanets.
Yes, please. That's a good
So,
solution because we are finishing. We have only 8 minutes. Okay.
Yes, give me now, give me a moment because I.
No.
Oh, here
Don't
is
worry.
she is. I think she is here. Breezy, are you there?
Yes, I am.
Okay.
So sorry.
Okay. Well, then
we have just a few minutes, Breezy.
Yes, you have few minutes.
Okay.
You can share your screen directly.
Oh, okay. Okay, great. Let me open it. I'm so sorry for the delay. I thought I still have time, to be honest.
Yeah, but yeah, well,
okay,
in any case, don't worry.
Share screen. Okay. Okay, can everybody see?
Yes. Not in full screen, please. Can you put in full screen?
Yes, of course.
Okay.
Everything looks okay?
Yes, perfect.
Great.
Go on.
Okay, so I wanted to show you the NASA exoplanet catalog, and I wanted to, when you have time to look at the catalog, after I show you how to do it, then I want you to kind of do an experiment and try to see if from all the planets you see there, you're able to find the planet Earth 2.0. So you go to the website, which is called Exoplanet. Actually, if we click here, I can send the link in a little bit because I know we're in a rush. And in that page, you find all the information from the planet. Here, for example, right underneath, you find the confirmation exoplanet. So the number that is most recently have, because we keep finding planets constantly. Then we have the star count. So around how many stars have we found those exoplanets?
Sorry, Breezy, you changed the slide or not?
No, not at all.
Okay.
Yes, I did. No.
But we cannot see the next slide.
Yeah, sorry. Let me try again. I don't know why it does that sometimes.
Well, in any case, you need to change the software.
Can you see the second slide?
Okay, yes.
Thank you. Good. Okay, so we have the page of the exoplanets, which here are 2 pages. Here would be the first one, and you can find in this page the amount of exoplanets that has been confirmed. Also, how many stars have we found exoplanets in, because some stars have more than one planet. And then we have here the latest planet that has been discovered. You can click there also and see information about that planet. Then if you scroll down in that page, then you will find a site that is called the Exoplanet Catalog. And once you click there, you could find information and the list of the planets and more detailed information about each one of those planets. And once you're there, then you can try to see, well, you see all the information from the telescope that it was discovered with, the type of star that it goes around, the habitable zone of the planet. You see a lot of information that, depending on what you want to do with that information, it's relevant. And from the telescope also it was taken. Now, one of the things you can do to look for that planet Earth 2.0, right? We need to think what would it take for a planet to be habitable for us. And So one of the things we need to think about is the distance from the planet to the star. This distance varies depending on the type of star it is, because if the star is larger than the habitable zone, it's a farther distance. So depending on the type of stars, where should it be to have that good distance where the water could exist potentially in liquid form? So the habitable zone of the star. Also, we need to consider the atmosphere of the planet, the magnetic field, and the location in the galaxy. Because not only the distance from the star is what matters, we have found planets that are in the habitable zone of the star, but that doesn't imply that the planet can host life. We need to take into account also the atmosphere. Both Venus and Mars are in the inner and outer edges of the habitable zone, but they cannot host life because the atmosphere they have. Venus is a great example for us to study because Venus teaches us what happens when we have too much of greenhouse gases. Greenhouse gases are good, but in excess, they're bad, as we can see in Venus, because they heat up the planet a lot. And in the case of Mars, we have a very interesting situation where we don't have a magnetic field. And so Earth has a very strong magnetic field. So when we look for a planet that could potentially be habitable for us, we need to think about magnetic field as well, because the magnetic field is there to protect the atmosphere. In the case of Mars, there's no magnetic field, and so the solar winds blows out all the atmosphere. And then the pressure of the atmosphere is very low. So it's very thin, the atmosphere. And we test that in one of the experiments of the NASA program, where you can test the atmosphere of Mars with the syringe and the water and the hot water. So all those things need to be taken into account, not only the distance from the sun, not only the atmosphere itself, also the magnetic field. Another factor that is very important are the distances in space. And we can take a look at this when we look at this activity that NASA has, where we can see the distance in the solar system. Now, if we extrapolate that to distances far to the closest exoplanet, we realize that we need to travel at least 6,000 years. If we do that using a constant speed from the man-made fastest object we've built, which is Parker Solar Probe. By doing that, we would take 6,000 years to get to the closest exoplanet. So it's very, very, very far. And if I have a little bit more time, I'll read these, but if not, I'm just going to leave it here. And thank you, everybody, for the attention. I cannot hear you, Rosa.
Thank you, Brisi. Do you want to show the NASA website?
Yes, I have. Great.
Yes, no, thank you for this, because we need to transmit this kind of message. It means our planet is not replaceable. It's the only one we have. And when we publish the discoveries about the exoplanets, the people believe that it's very easy to travel.
Yes.
These new exoplanets. And when the newspapers mention a second Earth, all the people believe that the second Earth is like the Earth.
Yes.
And is nothing comparable with our planet. And this is a message we need to transmit.
I agree. I think it's good to keep studying it. It's important for science, for knowledge, for knowing, but we don't need to get confused with that. We have co-evolved with planet Earth. So the atmosphere and the humans and everything living here, the plants, everything, we have co-evolved together. To get that kind of balance, we need to be in that place for a very long time. So even if we find a great candidate and we don't take into account the distance, it is almost impossible to be able to survive anywhere else, because we have co-evolved together. So, and then who would we take? It's a hard question. It's a very philosophical question, so I'll stop. But okay, so this is the website of the exoplanets. You can see here science.nasa.gov exoplanets. I'm sure I can copy this in a chat chat, or you may all have it maybe, but I'll
Yes,
put it.
I can do that.
Okay.
Continue.
So in this site is where we see the latest amount of confirmed exoplanets, because we have many candidates that are planets that have been observed and that we think may host a planet or may be an exoplanet. But once they appear here, it's because they have been confirmed to be an exoplanet. Then this is the amount of stars, as I mentioned. And here you see, I think I did this screenshot yesterday or the day before, and already it has changed. Now that you discover, it's another one. So if we were to click here, then we can find information about this planet. Of course, this is not an image of the planet. We cannot take a photo like that of the planet, but this is an artistic representation based on the information we know of the planet. And so here are information on that planet. And this is an example of the kind of information we can get. I'm going to scroll down so I can show you the actual catalog. There's a lot of interesting articles over here. But if we scroll down, here we can find information about the type of exoplanet. Let me see, because it's here. Exoplanet catalog. So once we scroll down, we can see the exoplanet catalog. We click here, and here we can do a search depending on the type of information we're looking. Maybe we're looking for a specific planet type, or a specific discovery method, because there are different discovery methods. Then maybe we are looking for a different specific mission. So, and if not, we can search the name here, or we can just look at the information of the planets from here. We can scroll down, and there are 441 pages that we can take a look at planets. And if we click in one of them, is what we saw before. I think this is the one we click. So let's see.
Yes, remember for everyone that NASA is proposing a list, but the idea is if you want to go deeper in the full list of possible candidates for your exoplanet, you can search something inside the NASA website, which is very, very complete.
Yes. Anything in particular that anybody else wants to see?
No, well, as you want, what you consider would be important. Perhaps if you click inside the different resources for each exoplanet, you can see the orbit, and you can see the atmosphere and the star and so on.
Yeah,
Yes,
actually,
there.
you mean
Yeah.
these ice on exoplanets? This here you can find a lot of information as well in a visual way, which could be really interesting for maybe a younger audience. Actually, for everybody. I enjoy seeing this. But
Yes, that's right.
let me just move my screen so I
If
can.
you click to the point, the orbit is just to the right, in the middle. Yes, the orbit, and you can see everything about this system,
Yeah.
the exosystem.
Yeah, so in this case, it seems we can see 2 planets at least discovered. I don't know anything about this planet. Okay, I'm just repeating what I can interpret from here. And then this seems to be the habitable zone, which is the place where water, potential liquid exists. And this is the start right here.
Exactly.
And it's located at 295 light years from here. So a little far.
Far away.
Okay, and yeah, also here, I guess we can get quicker to the star if we were interested. This out here, we learn about the type of star. This is a G-type star, so it's like the sun, more or less. It's too faint to be seen. Wow, I'm sorry, I can't read. Seen with the unaided eye from Earth. Okay, so yeah, for this we would need telescopes.
The only limit to use this kind of resources is you need an internet connection, of course. But well, the tools are available for use in general. So try to mix the hands-on plus the technology things and produce your own report, of course. Okay.
Maybe one question can be, I mean, how much how much does the website give you any categorization by itself? I mean, is any categorization in terms of habitability, or is there any on the website itself? Is there any categorization in terms of of ability characteristics of the exoplanets.
So
Has any,
habitability.
I mean, in terms of characteristics, is there any categorization on the website itself that these exoplanets are within the habitable zone, or these have magnetic fields? Is there any categorization on the website itself, or you have to just go through the data yourself?
Well, the thing is that, for example, in the case of the magnetic field, that probably requires a different kind of studies. So unless it has been particularly studied for that, I don't think it will be in this catalog right here. In the terms of atmosphere, sometimes like in this page, what you can see is information about the discovery method and if the planet has been confirmed. But I'm sure that when because once the planet is confirmed, sometimes we need a different telescope depending on the method that it was discovered with to study the atmosphere. So it's a different study sometimes. So I don't see information about that in this case, in this planet, for example, here. And I don't expect necessarily to find all that information, but probably if we go to a known planet that we know it has been studied, maybe there's a click to where more information can be found. I don't know, Rosa and Beatriz, do you know? If you can find, let me see. Maybe one of the first planets discovered, right, that we know more information about. Let me see what we...
Well, I don't remember exactly where is it. This is Kepler, but
this is Kepler,
it's
but it
okay.
was at the beginning, so I'm assuming it was discovered a long time ago. Again, an assumption, not a fact. I don't know. But this was discovered with Kepler, maybe. But I don't see information on the atmosphere right here.
No, bro. I was just checking whether there is any categorization on the website itself. We'll have to go through this here also.
Yeah. Yes, because some of them have not been studied for that.
Yeah.
This is a catalog. But for example, in here, it's telling us Kepler B is a giant exoplanet that orbits F-type stars. And its mass is, and it takes this how many days. So it gives you information, the information that we know of the planet. It's given it here.
Right. Thank you.
Of course.
okay. Well, Rosa?
She's muted. Rosa.
Sorry, I said that I think that the best way is that all of you explore this website because you need time to invest and to discover and to enjoy the information there. I am very happy that to say that was a pleasure for all of us, especially for Beatriz and for me, that you participate in this meeting. Thank you very much. I'm really sorry because we are a little bit later, but you know that was a good idea to try to visit a little bit this website in order that you enjoy to try to do in the future. Okay. Then thank you very much to everybody, and please continue working with us. You are NASE. Really, all of you are NASE. Without you, we cannot organize anything. And we are interested to continue promoting astronomy in all the countries, at all the levels, for all the students. And please enjoy exoplanets. Be sure that it is not possible to find, or it's not easy to find a planet B, but in any case, it is absolutely very interesting to discover more and more about different exoplanets. Thank you for participating, and see you in the future in following courses and following meetings. And please enjoy astronomy with all of us. Thank you.
Thank you for your energy, Rosa, and
Thank
all
you,
the
Paul.
organization.
Thank you. Bye-bye.
Thank you, Ricardo. Bye.
See you in October. In October,
Yes,
the closing ceremony. Bye-bye.
Yes, please. But before you prepare activities with your students. Thank you.
Yeah.
Bye-bye.
Thank you very much.
Thank you.
Thank you.
Thank you.
Bye-bye.
Bye-bye.